Alright guys, welcome back. So here we are for a new episode of this LeetCode series. Today we're going to do something different because I had a look at a few advices and information about these kinds of interviews, and I think that until now I approached the solutions for these problems in the wrong way, or at least not in the right way. So from now on, we will follow the following schema that I also wrote down. So basically, we will go through the trace. We will understand very well what's written here, as we were doing also before. And the first thing that we do is think about the simplest solution, okay? This we were doing also before, but what we were doing is to write down the simplest solution. No, that's not what we are planning to do. We will think about the best solution in pseudocode. So we will just concentrate on the idea, and then we will try to implement a better solution. And then only after we are ready, we write the solution down. And finally, we think about edge cases. So after these two cases are done correctly, we concentrate on edge cases that we cannot see, so we should think about them. Okay? So from now on, let's follow this schema. All right, so we are dealing with product of array except self. So given an integer array nums, return an array answer such that answer I is equal to the product of all elements of nums except nums I. So according to what I understand, we've got something like, there are a few nums, so 1, 2, 3, 4, and we want to return an array, that's right, such that an array nums, return an array answer, so nums is this. This implies that answer should be equal to, this first element should be 2 times 3 times 4, which is 24. Is that right? Okay, yeah, I think I understood correctly. 3 times 4, it's 12. This should be 8, and this should be 6. Yeah, very good, okay. And in the other case, if nums is equal to -1, okay, so we can also have negative numbers, -3, 3. Okay, so we cannot assume that the array is ordered. Okay, so in this case, it will be 1 times -3, so this will be -9. No, sorry, because there's a 0. My fault. Super stupid of me. Super silly. So this will be 0. So every number will be 0 outside of this number, which will be 9. Okay, because the presence of the 0 makes the array such that every other number will be 0, because 0 times any number is 0. This can be used later to simplify solution. I don't know if it will be useful at all. Okay, so now let's see. I suppose we can only work with integer. Okay, so we have an integer array, and we can also have negative numbers. And the array has a maximum length of 10 to the 5th, which is not that much actually. It's something like 100,000. So it's a lot of data, but not as big. Like it's not very big for like when you have to deal with a lot of computers. And nums can go only from -30 to 30. Okay, this is important. The input is generated such that answer I is guaranteed to fit in 32-bit integer. Okay, I see. Okay, so we expect that our numbers can be stored in a machine without being classified as infinite. And we can be sure that the elements contained in the array will be integers. All right. So the objective is to produce the array. Now, of course, the simplest thing to do. Well, I think it could be to simply say, all right, for each element here, I consider all the other elements. So I make a for loop and I say, okay, for this element, exclude this element from the array, take all the other elements, and multiply them. Okay, and then store this into an array. And this makes me think about this. Should we modify nums in place? No. We should we could create an answer vector. Okay, so this would work. So basically, we exclude this, we eliminate. So for every I in nums, we exclude the I. So let's say we exclude this value. We multiply all the numbers in nums, and we can do that with another for loop, I deduce. And once we multiply, so this will be O to the n squared, because once we have multiplied, we put the value into answer index I. So, but the problem is, in this case, we would have something like for num in nums, or better to say for e in n, given that our n is the length of nums, we would have something like right, so we have nums, let's say nums shorter, and then you define what is this nums shorter, which is basically nums without that value, and then you initialize another. So and then you say for num in nums shorter, and then you say something like you multiply, you create a product, you start the product as 1. You see what I mean? You initialize this product as 1, so you will have that you multiply this product by num, and so you get to the product, and in the end, you simply say, all right, so my answer will be answer of I will be equal to product. Now, I was really a bit like at the beginning of this exercise, I said that we would have started with the idea and without writing code. I basically wrote down code, but this was useful for me to understand exactly what to do each time. Okay, so this runs with a complexity. This can have a complexity O(n). These for num in nums shorter. So basically here it's like nums shorter as length n minus 1. So this is of length n. So this algorithm is of complexity O(n) squared. Unfortunately, yeah. Okay, so let's try to think about another way to approach this problem. So I want to so you must write an algorithm that runs in O(n) time and without using the division operator. Okay, this is important. I don't know why this is important actually, but we may use that. Okay, so from now on we need to calculate the product of each number. So let's think about the complexity of the problem. For sure you have to calculate a product. So if you want to calculate a product, you need for sure that the problem is O(n), because you need to calculate a product. No, sorry guys, I have an idea. So here you see, if you compute the product between 1, 2, and 3, you share the same, and then you compute the product with 2, 3, and 4, you are basically multiplying these three numbers and these three numbers, but two of these three numbers are in common, are 2 and 3. So if you compute this product, then it's not necessary that we recompute it. We can just take 1, 3 to 1, divide it by 1, and multiply it by 4. And this is the problem. We can't use the division operator. And this is a big problem, because another way to do that was just, I compute the product of all these numbers, and then for each product, I divide my numbers by, let's say, 1, and then 2, and then 3, and then 4, and each time I got the product that I have to insert in position I. Like, for example, here I need to do this product and then divide it by 1, and I would insert the value 1, the product divided by 1 here, and then here, and then here, and then here. This is super. The problem is we can't use the division operator. So this is not the right way to approach this problem. If we can't use the division operator, then how can we multiply, like even what I was thinking about at the beginning, like 1, 2, 3, if we multiply those, it's 6. If we multiply, and then I would have to both divide and multiply. So it's basically the total multiplication that I was mentioning, but in a worse way. So no, doesn't work. Unfortunately, I think that we have to think about a different way to approach this. Now, the point is, since the complexity must be O to the ON, this means that considering that we have to scan for each value, so for 1, 2, 3, and 4, and substitute those values with the right product, the product itself should happen in the O1 complexity. Because if the product happens with the ON complexity, then it can't be possible that it works. And we cannot assume that the array is sorted, so we cannot say anything about that. Okay, so let's think about this array. -1, 1, 0, -3, 3. So I have to compute this product, and I have to compute that with every possible combination. Now, how do I compute this product once and for all? Okay, what comes to my mind is that we have to multiply these values all together, because if we can't multiply them and divide, how can we do this product very easily? If I multiply these 4 numbers, I get to this value. Well, we can make use of the fact that we have a 0, maybe. But in case we do not have a 0, suppose we don't have a 0, so how can we use this information? Okay, you know what, guys? Let's use the hint, because we expect the interviewer to help us. So let's try to use the hint. Think how you can efficiently utilize prefix and suffix products to calculate the products of all elements except self for each index. Can you pre-compute the prefix and suffix products in linear time to avoid redundant calculations? Prefix and suffix products are something like, here we are dealing with an array like 1, 2, 3, and then we have high, and then we go to 5, let's say 5, 6, 7. So the prefix products are 1, 2, 3, and the suffix products are 5, 6, and 7. So I deduce that what they are telling us is to basically say, all right, once we are here, we always use this product, always, because we are moving to the right. And we are using this product, okay? So, for example, I is, of course, the product, like the value that we should insert at index I, actually at index I minus 1, it's 1 times 2 times 3 times 5 times 6 times 7. The problem is this is increasing, this is shrinking. So I could say, all right, so I start here and my suffix products is one, like it's, I can't use division. That's the problem. Because if I am here, I will have that there is no prefix product, but there's suffix products. And this I can calculate, this is an n time, the first time. Now the second time I'm here, the prefix, I can compute, but this is basically the one that we used before, divided by 2, but we can't use the division. That's the main problem. We can't use the division. We can't use the division. Though, what can we do? What can we do? Suppose that we are, okay, so something that we can for sure do is once we are in the middle, we can say, all right, 1, 2, 3, these are always there. So instead of calculating the product again, I can just say, all right, I have this temporary product. The next time I just multiply by 4. So this part of the product can be always computed in linear time, like not in linear time, sorry, in O1. Like each time the product requires one iteration, multiplying by a number. First one, then two, then three, and so on, okay? The problem is on this side, because on this side, instead, it's shrinking. It's shrinking. We compute the product and then we divide. But wait a second. What if we have something like, then I, 5, 6, 7. Okay, 6, 7. So for example, we are here, and then we go here. Well, in this case, the value that we should exclude from the product is I itself. So we can make use of it, maybe. Is I itself 5 divided by I? I don't know, guys. I don't know yet. I know how to diminish the complexity to n squared divided by 2, because I know that this can be computed in the linear time. But this, without using the division operator, not sure. All right, guys, just because it's the first time that we use this new approach, let me use also hint 2. And from the next time on, we'll work on the solution with dedicating much more time. Can you minimize additional space usage by reusing memory or modifying the input array to store intermediate results? I think that this is related to the follow-up. So it's not useful. Okay, fantastic. What can we do? All right, so let's just repeat what we are doing until now. So we start with 1, 2, 3. Okay, so let's see that our starting array is the following. 1, 2, 3, 4, 5, 6, 7. Okay, we start here. We compute this product. This product cannot be reused because we can't divide by 2, unfortunately. Is that right? Without using the division operator. But you know what we can do is to compute all the products. Can we do that? I don't know if this is actually better than before, but we can say, you know what? I will computing all the products in here is n squared. Is all n squared because we are literally taking all the couples into account. Even more than n squared. We are doing. It's not what we want to do, guys. Really, it's not what we want to do. Well, okay, I think I've got something. I have an I, which moves from 1 to 7, and then I compute this product, and then this product. I was thinking about storing this product to increase, but what if we compute it? We do that n times for e in nums shorter. Yeah, but it's the same. It's the same. No, guys, I have no clue. Really, like, I don't know how can we escape the O n squared. All right, guys, I looked for the solution. Yeah, okay. It's not going really well this time. And actually in the past few times, I have to be more strict and I have to stay more on the solution. But still, I'm not too sure that at this time, which I consider still the beginning, we should spend so much time thinking, because sometimes I think these kind of solutions are super, in a sense, they're super trivial for an expert software engineer. And I expect that after seeing some solution, so not only finding, but also after seeing some solution, you just develop sort of intuitions for these kind of problems. Or at least when I did the Math Olympics, just seeing and reading a solution was enough to be able to solve an exercise like that, similar to that, to develop a sort of intuition in the future. So I still believe that looking at the solution at this stage is considerably useful. So the idea is that you should look at what's before I and after I, but then you should not try to do everything at the same time. So the idea is you have this array, and then what you do is to simply, you suppose that I is here. Suppose that you start here, okay? You start at 1, okay? So you simply say, all right, so my value in the answer array will be this product. And this product, sorry. No, this is super stupid. The value in the array will be like basically 1 or 0. Okay, we can start with 1. Okay, so if I have nothing on the left, I multiply by 1, because 1 is basically the, in multiplication is the identity operator. Okay, then I move here to the 2 and I multiply by 1. Then I move to 3 and I multiply by 2. All right, do you see what we are doing here? Then I move to 4 and then 5 and then 6 and then 7. At the same time, once we are here in a new for loop, we multiply by 1, 7, 6 times 7, 5 times 6 times 7, 4 times 5 times 6 times 7, 3 times 4 times, and blah, 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 and 2, 3, 4, 5, 6, 7. So basically we do the prefix and the suffix in 2 different for loops. So the idea is basically that for E in N, you have a sort of like, you just say, all right, so I want answer of I to be equal to, I just multiply, I define a prefix and the suffix. So I would have something like prefix equal to 1 and suffix equal to 1. And then it's simple. I don't need to do all the product. I can just say, all right, answer I will be equal to my prefix times I. All right. And so, of course, in this case, it will be 1. But then, with the increasing I, of course, include, but with this, I am considering also the number itself. Okay, I think, guys, actually, I didn't fully understand the solution. And this is good, because it's like I got an int. So, if I start from this number, and I multiply each time the prefix times the number, I am getting to the different prefix and suffix for nums I. So, for example, I can say that answer I is equal to prefix times nums I. Here we need range. Now, the problem that I see here is that here, for the first answer, there is no prefix. So we want basically not to include this. So we say answer I plus 1. So we take this value and we multiply that by nums I. But we need to update the prefix. So the idea is that we want the prefix to be updated, and then we multiply it by the prefix. You see what I mean? Okay, great. So once we're here, you simply continue until you reach here, until you reach the end, and then you simply do it again. So you copy this and you repeat this. So you say, all right, for I in range n minus 1, I do the opposite. So I say suffix is equal to suffix, but this time I do that the other way around. So I do something like n minus 1 minus I. And then I change. You see what I mean? So it's like n minus I. Minus 2 at this point. Yeah. Or maybe I can go with range 1n, this doesn't matter, so that I can say n minus I and n minus I minus 1, but it doesn't matter. It doesn't really matter. What matters is that once I reaches n minus 1, answer 0 is updated with the prefix that arrives until nums 1. And in the end, you can just return answer. Okay, guys, so I think this is the right solution. Well, let's try it at this point, which can be easily done by simply uncommenting this code. And we see what happened. So instead of testing it, and here we return our answer. Of course, here we need to define prefix and suffix. Here this can be eliminated. This can be eliminated. So we have our two examples. And of course, we want to define an n, where n is equal to len of nums. And yeah, everything is great. We just need to test it, but we will not test it, as I said at the beginning of the episode. We will test it directly with our reasoning about the input. So let's say that we start with 1, 2, 3, and 4, okay? So in this case, the length of n is equal to 4. All right, the prefix is equal to 1, and the suffix is equal to 1. Now, for I in range n minus 1, this means basically that I goes from the n minus 1 is 3, so it's I ranging 0, 1, 2. Okay, and this is good because we want I to be equal to 1, 2, and 3. Okay, so prefix is equal to prefix times nums I. Of course, here we are multiplying answer I plus 1 times a prefix, but we didn't initialize it to an answer. An answer is a vector 1 times n. Okay. Now, prefix is so basically we multiply prefix by the num. So in this case, prefix is equal to the first case. Prefix is equal to 1. In the second case, once we update it again, it will be equal to nums 1 is equal to 2, so it will be 2, and then again it will be equal to 6. Okay, so here, answer of I plus 1 times prefix means that the first time the vector will be something like, okay, so it starts with 1, 1, 1, 1, and it is updated by multiplying this value, so the value at index 1, by 1. So nothing changes. The second time, the answer at position index 2 is multiplied by 2, so it will be this. And the third time, it is multiplied by 6. Okay? Great. On the other hand, now we've got with I that goes from 1, 2, and 3, because n is equal to 4. And the suffix at this point will be, we start with 1, and for n minus I, so we've got nums of position n minus 1, so this is 4. So we've got that suffix is equal to 4. And then we multiply this by n minus 2, which is 3. So this becomes 12 and then 24. All right. So this is gonna be, we start with 1, 1, 1, and then we multiply 1 by, sorry, no, we multiply answer n minus I, where I is our index, so it starts with 1, so n minus 2, so basically we are updating this value, and this value is gonna be 4, and this is gonna be 12, and this is gonna be 24. And then, of course, what we have to do, because this is what I missed at the beginning, of course we have to multiply. Oh yeah, that's super wrong. Let's say answer first and answer second. Okay, this is super stupid, but I forgot to put together these two answers. And then again, I say for I in range n, simply say, let's say that answer, this is equal to 1 times n, and answer is equal to 1 times n. All right. Let's say that answer now is equal to answer first I times answer first second I, and we continue. We simply continue, and until the end, and we reach a solution, and this should return answer. And I think we've got it, because once we multiply 1 times 2 times 6, and we multiply this, we get that this should give us, as a final array, it should give us 24, 12, 8, 6, which is exactly what we want to get. Now, before saying that this is the right solution, let's think about potentially some edge cases, okay? So suppose, for example, that we're dealing with 0, 0, 0, 0, right? So prefix times nums I is gonna be 0. Is this a problem? No, because you always multiply times 0. So the prefix will be 0, and then you're great. We can also even add something like if a prefix is 0, then stop. I don't know if this would increase the performance, not that much. It's just something that we could add, and it's the same for suffix. So no. What if the array is empty? So if the array is empty, we can just say, hey, if n is less than, well, actually, if n is equal 0, but we have a constraint. We know that nums is greater or equal than 2, so we don't need these. We are okay. In case the array is of size 2, well, doesn't matter, it works pretty well, because for I in range 1, it will be just a number, and it's absolutely fair. Yeah, guys, I don't see any problem, so I think we can test at this point. Okay, guys, fantastic, it's wrong. What's the problem? This is super stupid. It's just that we forgot I here. Okay, let's try again. 6, 6, 12, 6. You're right, because here we do not get 24, 12, 4, 1. Or actually we do. Okay, you know what? Let's just say that here we multiply the suffix and we multiply the prefix just to simplify the syntax. Yeah, guys, but why are we using answer first, answer second, if we are dealing with a multiplication? I was wrong when I said that this was needed, actually, because we are already taking this into account because we are dealing with a multiplication. It's not a summation. Let's try again. Doesn't work. Why? Because I'm stupid, because here we need to put suffix. Okay. Okay, yeah, okay. It works. Now, it's not done yet, because the follow-up question is, can you solve the problem in O1 extra space complexity? The output array does not count as extra space for space complexity analysis. Now, what's the problem here? We have n, we have prefix, we have suffix, we have answer first, answer second, and answer. But this is not needed anymore, but we still have answer. Well, answer is the output array. I'm using prefix, I see, but prefix does, like, you just take O1 each time of memory, because you just have to store two elements, prefix and suffix. But this is already O1 solution. Yeah. I think it's already a O1 solution in space. Is there a way to check here? Yeah, can I analyze complexity of memory? Space complexity ON. Why is this ON? Well, guys, I think it's wrong, because it says analyzing complexity including the output. So yeah, I think this is correct. I think this is the correct solution. Yeah, guys, thank you very much for joining me in this video. I think I have to train a lot. I will keep solving problems, but I think this way of solving problems, so basically we first start from understanding very well the description, then we think about what we want to achieve, we think about a very simple approach, we don't write code, or we write some pseudocode, and then we try to find a more efficient algorithm, and then once we're ready, we write it down. Okay? Great, guys. So thank you very much again for watching this video, and see you in the next video. By the way, I just wanted to make you aware that all these videos that I am recording are so dense, because I am recording all of them while preparing for this interview. So it's like I will publish, I don't know how many videos just recorded in a few days. Anyway, guys, I sincerely hope that this series will be useful for some of you, and in general you could appreciate it, because I'm really enjoying the fact that I solve algorithms along with you, because it's really helpful for me and I really enjoy it. It feels like I am with other people. So thank you very much, guys, and see you next time. Bye bye.